Last we stopped was understanding what is Oswald's dilution law. As per Oswald's dilution law, if the concentration of solution decreases, then the alpha value will increase, dissociation will increase, and hence you might start getting more number of H plus ions. This is what is Oswald's dilution law suggests. So on dilution, more ionization. And using that, we can figure out there are two important formulas we got. One is a formula for alpha, that is degree of dissociation. Second one is how much will be the H plus ion concentration, which is equal to under root of KAC naught. Or if you write the same thing in terms of pH, we got this as half of pKa minus log C naught. So if you want to compare acidic strength of two acids, you can always assess by their Ka value. What is Ka? Ionization constant of acids. By definition, what is Ka? Ka is products concentrations by reactant concentration. In product, we have H plus and X minus, divided by reactant, we have Hx. Now, for an acid, if it is more acidic, you will address that it has to give more amount of H plus ions, which means this numerator value. If the numerator value is higher, what do we expect with the Ka value? That should also be higher. Therefore, higher the Ka value, stronger is the acid. Hence, I can say acidic strength increasing depends upon increasing Ka value or decreasing pKa value. Because if I say Ka value is increasing, automatically pKa value will be decreasing. We learned that pKa by definition is minus log of Ka. So if you can see Ka value is increasing, so this entire value will start decreasing. Clear? Now notice the list or family of compounds, different family of compounds and their range of pK values. Okay. For example, most of the alkanes generally have their pK value between 48 to 56, which means this value suggests that such a high pK value represents a very low H plus ion concentration. And if it is very low H plus ion concentration, that means its acidic strength is extremely weak. Thus, alkenes are such family of compounds which have least acidic nature. Next comes alkenes. The general pKa value for alkenes ranges from 44 to 48, which also suggests that they are very weak acids, but relatively better than alkanes. Then we have amines. Amines are between 38 to 44. So we can say that is also relatively weak acids, but amines are still slightly better than alkanes and alkenes. Benzene, to break this H plus, the pK value for that is 43. So definitely it is better than normal alkenes and alkanes. Correct? So this one, benzene will have slightly better acidic strength than alkanes and alkanes. Then toluene. Toluene will have even more slightly better acidic nature than benzene. Then ammonia and H2 both has exactly pK value of 38. We are expecting to remove H plus ion from ammonia. We are expecting H plus ion to remove from H2. Then their pK value is around 38. Now, notice alkynes. Alkynes as a family, its range is from 24 to 26. So alkynes are relatively more acidic than ammonia, H2, toluene, benzene, amines, alkenes, and alkanes. Similarly, alcohols range between 16 to 20. And as it comes to water, water is around 15.7, Methanol, on the other hand, is slightly more acidic than water. This is the only exception. The only alcohol which is slightly more acidic than water is methanol. This is an experimental value, so do not worry about trying to understand that right now. When we discuss, more in detail in GOC, we'll discuss there. Phenols. Phenols, the pK value will be ranging it close to 10. Then we have carbonic acid. Okay. Carbonic acid, I'll just change this value, slight change in the value there. This is carbonic acid will have somewhere around 5.8 and above. Next, when it comes to carboxylic acids, okay, that means all organic acids, their range changes from 4.5 to 5.5. Got it? And if it is benzoic acid, exactly 4.18, formic acid 3.9, sulfonic acid -3 to -5, which means minus itself suggests that it's a very, very low pK value, which means very high Ka value, which means it is highly acidic. So all sulfonic acids are generally more acidic. Then HCl, HBr, and HI, you can see the values only further becoming more and more negative. So that suggests out of the given acids, usually HI is the strongest acid, whose pK value is -11, which suggests that it is highly acidic. Picric acid is one. Okay, picric acid is this one, where we have phenol with NO2 at these three positions. This is called picric acid. Sorry. Then we have HCN. The pK value is around 10. For H2S, the pK value is around 7. HF, it is 3. So this is generally the acidic ranges from various functional groups, various family of compounds. Got it? Over time, not today, immediately, but over time, slowly start learning how to remember this, correct? It will be much useful if at all you could, remember this part. Clear? Check out. Now, just like how we did the case for strong acids, I mean, sorry, generally for weak acids, how we calculated or identified the formula, the same logic applies even to weak bases. So when you have weak bases, you can apply the same logic, figure out a formula for that as well. Okay. So let me show you how we can figure out the formula there. Suppose if BOH is a weak base, we expect it to give B plus and OH minus. And if OH minus value increases, that means the Kb value increases. Kb value increases means it is a stronger base. That's how we relate. Now imagine at time t equal to 0, concentration is C naught, and at equilibrium, this will become C naught minus C naught alpha. This will become C naught alpha, and here also it will become C naught alpha. Okay, so which gives us Kb value will be equal to C naught alpha whole square divided by C naught minus C naught alpha. So one C naught will get cancelled. So we'll get this as C naught alpha square minus 1 minus alpha. And we learned that for most cases, for most weak, for most weak electrolytes, those electrolytes may be acids or bases. We consider alpha is far less than 1, implies Kb will be equal to C naught alpha square, which implies alpha will be equal to Kb by C naught. So it's the same formula, same Oswald's dilution law. but this time we are doing it for base. And hence, OH minus concentration will be equal to, C naught alpha, which is equal to C naught into under root of Kb by C naught. That is under root of Kb C naught. Clear? So here, OH minus concentration, if at all I write in terms of POH, POH will be equal to half of pKb minus log C naught. So you can see the formula is the same. Only difference is instead of H plus we have OH, and instead of pKa now we have pKb. The derivation is also the same. Clear? And I can say that as pKb value increases, then Kb value decreases, implies basic strength decreases. Basic strength decreases. Clear? And you can notice that for bases, you know, strength is directly proportional to OH minus or directly proportional to Kb and inversely proportional to pKb value. Okay. So I think all of you understood this, how to represent Oswald's dilution law for both acids and bases. Finished, everybody? Right. Notice next part is about understanding relation between pKa and pKb of conjugate acid base pair. You know that how we have conjugate acid bases, how we can relate the conjugate acid and base with respect to their pKa and their pKb value. Now, what does pKa here stands for? That means it is the minus log of Ka. So how do we get Ka value? Now, let me take one example here. Acetic acid. Acetic acid is a weak acid. It will ionize into CH3CO minus and H plus. Its Ka value can be written as product's concentration by reactant concentration. Similarly, what would happen if it is a conjugate base? Conjugate base is CH3CO minus, and that if at all you keep it in water, correct, and it will take H plus from water and convert into CH3COOH plus OH minus. See, it's increasing the OH minus concentration. That is what we need eventually. I can say that conjugate base here is increasing the OH minus concentration in water. So hence, this is the Kb value now. So by definition, what is Kb here? Kb is concentration of CH3COOH and OH minus divided by CH3COO minus. This is what we have in relation. Okay. So when you have a solution which should have an weak acid and its conjugate base, both exist in these two equilibriums. Okay. Weak acid is trying to give you strong base and H plus ion, while that strong base is trying to react with water, releasing OH minus. So these two will coexist. These two equilibriums will be coexisting. Now, how do we relate them? Let's multiply Ka and Kb. So if I multiply Ka and Kb, what do I get? You could clearly notice that the CH3CO minus will get cancelled. CH3COOH will get cancelled. And what is left here is H plus ion concentration into OH minus ion concentration. And we know that H plus into OH minus concentration, we define it as Kw. So therefore, for a conjugate acid-base pair, its Ka value and Kb value can always be equal to Kw. Or if I write in terms of pKa, I can write it as pKa plus pKb will be equal to pKw, which is equal to 14. For example, for example, the pKa value of acetic acid, that is CH3COOH, is 4.7. Then what will be the pKb value of acetate ion? Acetate ion is CH3CO minus, which is the conjugate base. That has to be 14 minus 4.7. So that is equal to, okay, 14 minus 4.7. So hence that is equal to 9.3. So 9.3 and 4.7 are the conjugate acid base values, pK and pKb values for any acid. So which means if you know the pK value of certain acid, automatically you know that what will be its pKb value of the conjugate base. Clear on that, everybody? So this is how pK and pKb can be related. Similarly, let me give more examples. These are more relatable examples because we'll come across a lot of times. Ammonium hydroxide or simply ammonium aqueous, both of them are same. When I write ammonium hydroxide or ammonium aqueous, pKb value for that is 5, which means pKa value of ammonium ion, that is NH4 plus, is equal to how much? 9. So for ammonium ion, the pK value is 9. Got it? For example, if you are comparing an acetic acid with an ammonium ion, which is more acidic in that sense, CH3COH. That is, if you compare the acidic strength, clear, of CH3COOH and NH4 plus. If you compare these two, it implies that, acetic acid ACOH is more acidic than ammonium ion salts. Okay, this is more acidic than ammonium ion salts. I guess all of you understood this point. This is a very, very important thing. While a lot of questions will try to confuse you, sometimes giving pKb value instead of pKa value. That is something for you to evaluate because their conjugate acid base will always be related with respect to pKw. Has everybody made a note of it? Right. What is this question? Find the pH of the mixture having HCOOH and another HCOOH of different values, different concentrations. Okay. If we have same acid of two different concentrations, got it? Same acid of two different concentrations. So you are supposed to calculate first what is the C naught of HCOOH. Clear? So since it is the initial concentration, and I'll take C1 of first acid, HCOOH concentration is, let's say, 0.2, and C2, which is the concentration of the same formic acid of the second solution, is 0.1. The volume V1 used here is how much? 100 ml. Okay, and volume V2 here used is 400 ml. Now, how do we calculate the initial number of moles? N1 is the number of moles of this acid. The number of moles of this acid is 0.2 into 100, correct? Concentration into volume will give you number of moles. So number of moles is 20 milli equivalents. Here also, number of moles of HCOOH will be equal to 40 or 400 into 0.1, which is 40 milli equivalents. So now you can see these moles, because both of them are same acids. So the total number of moles of HCOOH will be equal to 60 milli equivalents. Hence, And what is the total volume here? So total volume now will be equal to 400 plus 100, which is 500 ml. Now we know the total number of moles and we know the total volume. So what will be the final concentration? So final concentration after mixing will be equal to total number of moles by total volume. That is equal to 60 milliequivalents by 500 milliequivalents. So that is equal to 6 by 50 molar M. 6 by 50 M. That is the concentration of final solution of formic acid. Okay, correct. So we can write it as 6 by 50 or 23 by 25 molar. Now, since it is a weak acid, guys, directly apply the formula. So pH is equal to half of pKa minus log C naught. That is equal to half of pKa value is given, I guess, that is 3.9 minus log of 3 by 25, which is equal to half of 3.9 minus log 3 and plus log 25. 25 is 5 square. That is equal to half of 3.9 minus 0.47 or 48. That is a value of log 3, correct? 0.48 is a value of log 3. That uh, plus 2 times of log 5. Log 5 is always 0.7, which is 1.4. So that is equal to total, I'm getting it as 5.3 here plus 1 minus 0.48. So 5.3 minus 0.48 divided by 2. So that is coming as 2.41. So this is the pH value of the mixed acids together. I hope all of you understood this case, how to find the pH of any solution. Okay, right. On the similar lines, let's do the second one together. Everybody, check out. Calculate the pH of the mixture having 20 ml of 0.1 molar MgOH twice and 80 ml of 0.05 molar MgOH twice. Logic is the same here. So check this out. How much will be the KB value? Sorry, here, please change this part. KB value of MgOH is 10 raised to power of minus 6. KB value is 10 raised to power of minus 6. Now listen, there is only one problem in here. That is, instead of giving one OH minus, it will be dissociating into two OH minus. So let me do without using the formula. That is, KB value will be equal to Mg2 plus ion concentration into OH minus ion concentration whole square, that divided by MgOH twice, sorry, concentration of MgOH twice. This is what we have. Okay. You know that when dissociation happens, okay, for example, if the concentration of this is C naught initially, and if this will become C naught minus C naught alpha, so then this will become C naught alpha and this will become 2 C naught alpha. So that will be the KB value here, correct? And as usual, KB in this case will be equal to C naught alpha into 2 C naught alpha whole square divided by C naught minus C naught alpha, correct? And alpha we consider to be much less than 1. So therefore, KB value now will be equal to C naught. 1 C naught will get cancelled. So we will have 4 C naught square and alpha cube, that divided by 1 minus alpha, correct? I mean, 1 minus alpha can be removed out. So this is what you will have. So 4 C naught square into alpha cube. Got it? So from here, from the given values, you can find out what is alpha value. And once you know the alpha value, what will be the concentration of OH minus? So OH minus concentration will be 2 C naught alpha. So that is equal to 2 into C naught multiplied by the alpha, which you must have calculated from this point. Clear? So now using this formula, let us first calculate what is alpha. Got it? So therefore, alpha value, sorry, alpha cube KB is equal to 4 times of C naught. Now I need to find out what is the initial concentration after the mixture. So how do we do that? So this C naught is that final value which is coming from C1 V1 plus C2 V2 divided by V1 plus V2. So C1 V1 is 20 into 0.1 plus 80 into 0.05, that divided by total volume. Total volume is 100. Clear? Right. So therefore, how much we are getting here? So this is 2 plus how much we have? 4 divided by 100. So which is 6 by 100 or 3 by 50. Correct, Radhika? So this is 3 by 50 molar. You got to use this concentration term here. So that is 3 divided by 50 whole square multiplied by alpha cube. So therefore, alpha cube will be equal to KB into 50 into 50, right? That divided by 3 into 3 into 4. Okay. KB value is 10 raised to power of minus 6 into 10 raised to power of 2 into 25 into 25 divided by 9 into 4. Okay. So that makes it 10 raised to power of minus 4 into 25 by 9 into 4. Okay. These are the values we have. Clear? So let me just use this calculation value here. So that is 25 divided by, and what I'll do to make it more simplified, I can just use this as 2.5 instead. So 2.5 divided by 9 into 4 into 10 raised to power of minus 3. So it is 2.5 divided by 4 divided by 9. So I'm getting this approximately as 0.07 into 10 raised to power of minus 3. Correct? And now let me take out the root for that. So cubed root of 0.07 is coming out to be 0.412 into 10 raised to power of minus 1 after taking the root value. So this is the value of alpha. This is alpha cube and this is the value of alpha. Once you know alpha, you can calculate what is the OH minus concentration as well. So OH minus concentration is equal to 2 times of C naught value. C naught value we have already calculated this as 3 by 50 multiplied by 0.0412. Okay, so 2 into 3 multiplied by 0.0412, that divided by 50. So which is coming approximately 0.005. This is the OH minus concentration. So what will be the pH here now? I mean pOH here now. pOH will be minus log of 0.005. Clear? So which is clear that it is 5, I mean log 5, 10 raised to power of minus 3 here. So 3 minus log 5. So 3 minus log 5 is 0.7. So 2.3. So pOH is 2.3, which makes what is the pH value? So 14 minus 2.3. Clear? So which is 11.7. So this will be the pOH value and pH value. So such cases, if you want to calculate the pH, first you calculate what is the pOH and then you calculate what is the pH. So please go through it once, everybody. Check if there is any doubt. I actually use this little bit more elaborative just to make sure that you understand how to evaluate alpha also. Okay. In the question, there was no mentioning of alpha, correct? So we could directly do without calculation of alpha also. That is, you can consider, that MgOH2 plus concentration and OH minus will be same concentration, isn't it? Clear, everybody? So if this is X, this will be 2X only, no? So there is a relation, direct relation, that these two are just, I mean, the Mg2 plus and 2 OH minus concentration, both can be related directly. So we can write if MgH concentration is X, what will be OH minus concentration? It will be 2X. So 2X whole square. So that makes it 4X cube divided by C naught, that is equal to kV. So directly calculate X. Clear, everybody? That is another way of finding out OH minus concentration without calculating alpha value. I suppose this solving is clear, everyone. Did everybody made a note? Samyak, did you check it out, beta? Did you write it? Right. Now, before going further into understanding what is the mixture of weak acid, strong acid, I want you to become more comfortable in understanding any type of acids, any mixture of acids, especially when they are strong. Okay. If you have strong acids, then how do we need to figure it out? Let's try to spend some time on that. Okay. Let me do this question. Check out. If your objective is to find pH and pOH of following cases, what are those? First one, 0.01 molar, okay, H2SO4, correct? H2SO4 is a strong acid. Now I'm writing everything for strong acid. So You can see that strong acid means we have H2SO4. You expect that to completely ionize into 2H plus ions plus SO4 2 minus ions. 2H plus and SO4 2 minus ions. Okay. So if this was initially 0.01 molar, now we expect that this entire thing will be ionized. So it will not be left anything. So it will convert into 2 times of 0.01 and this will be 0.01. Thus, you can notice that the H plus concentration present in the solution right now will be equal to 2 into 0.01, okay, which is equal to 0.02 molar. Hence, the pH value for this will be equal to minus log of 0.02. So, which is equal to 2 minus log 2. So, 2 minus log 2. So, you can see it is 2 minus 0.3 because log 2 value is 3. So, which is 1.7. So, the pH value is 1.7. The pOH value will be equal to 14 minus 1.7, which is equal to 12.3. Clear? So this is the H plus and pH and pOH of the solution. Is there anything which I did ignore here? If you please put some view on it. Okay. See, whenever you have, you know, acids been added to aqueous solution, we are forgetting that the H plus is always calculated for the solution. Now, let us try to make this as an important note that whenever you are writing H plus of the solution, that means you are expecting H plus is contributing from multiple directions. That is, H plus is coming from an acid which you have added, and H plus can also come from the water that you have already present. Agreed? Clear? If the H plus concentration coming from acid, listen up everybody carefully. If this is greater than 10 raised to power of minus 5 molar, okay, greater than or equal to also, sorry, greater than or equal to 10 raised to power of minus 5 molar, then ignore H plus ion concentration from water. Clear? So that means you will ignore this value here. That is how much is contributing from H plus, how much is contributing from water to the overall H plus you can ignore. But if the H plus ion concentration of acid is less than 10 raised to power of minus 5 molar, then don't ignore, don't ignore H plus ion concentration coming from H2. You have to write it as the sum of the acid concentration and H plus concentration coming from water. Now try to go back to the question and see that how much we are getting 10 raised to power of minus 2, which is definitely a greater value than 10 raised to power of minus 5 molar. That's the reason why we didn't take the contribution of water here. Agreed? Right, everyone? Now do the same logic even when it comes to OH minus. In case of OH minus also, if the concentration of OH minus is greater than 10 raised to power of minus 5, ignore what is coming from water, only consider it from the base. Let me show you with an example here. See, second one, 0.02 molar calcium hydroxide. Calcium hydroxide. If you want to calculate the pH of 0.02 molar calcium hydroxide, okay? Here, I'm giving you that hint that assume 100% ionization, which means expecting this to be a very strong base. So in that case, what we can write, that calcium hydroxide will get completely ionized into calcium 2 plus ions plus 2 OH minus ions. And if this is 0.02 molar concentration, everything will be dissociated completely to form 0.02 molar calcium 2 plus and 2 times of 0.02 molar OH minus ion concentration. So OH minus ion concentration of the solution will be equal to 0.04 molar solution, which is greater than, in the bracket, it is greater than 10 raised to power of minus 5 molar concentration. That's why we are not worried about how much is water contributing. Thus, POH will be equal to minus log of 0.04 value, which is equal to 2 minus log 4. So 2 minus log 4 value is 0.6. Thus, it is 1.4 value. POH is 1.4, so which makes pH will be equal to 14 minus 1.4, so which is 12.6. So this is a calculation from calcium hydroxide, everybody. Done? Everybody? Right. Now, let me give you one more slightly example of small mixtures. That is, if you have 20 ml of 0.1 molar HCl, okay, that plus 20 ml of 0.05 molar, you know, 0. Sorry, yeah, let me use that value, 0.05 molar NaOH. Now it is more of an strong acid, strong base acid, a strong acid and strong base titration. So both of them are mixed. Then what will be the pH of the solution? All right. So what do we expect as a reaction here? That is HCl plus NaOH. Both will interact to form NaCl plus H2O. Now how much is number of moles given here? 20 into 0.1. Here it is 20 into 0.05, which clearly mentions that this is 2 millimoles. This is 2 millimoles. And here we have 1 millimole. So it is clear that NaOH is in less quantity. So that is the limiting reagent. So 1 millimole will be left here. 1 millimole of NaCl will be formed and 1 millimole of water will be formed. So what is left over is the one which will contribute to H plus and OH minus, correct? So you can see HCl concentration now will be number of moles left divided by total volume. So how much is the number of moles left? 1 millimole divided by the total volume is 40 ml. So it is 1 by 40 molar is the H plus ion concentration, which means, because HCl is a strong acid, so HCl concentration will be same as H plus ion concentration, which is 1 by 40 molar. So pH value will be equal to minus log of 1 by 40 or log of 40. So log 40 means 1.6, correct? So pOH will be equal to 14 minus 1.6, which is equal to 12.4. So these are the values of pH and pOH for the solution. It is still sufficiently acidic. I guess this part is clear, everyone. Right. See the fourth one here. Again, do it simultaneously, everybody. What if I have a mixture like this? 10 ml of one normal HCl plus 20 ml of two normal H2SO4 and 30 ml of three normal HCl, HNO3. Okay. Assume all have alpha value 1, which means 100% ionization. They are all getting dissociated 100%. Whenever normality is given, first convert that into molarity. You know that molarity, what is the relation between normality and molarity? Normality is equal to valency factor into molarity, or that implies molarity is equal to normality by valency factor. So you can see molarity of HCl will be equal to normality by valency factor. Valency factor of HCl is 1 and molarity of H2SO4 is equal to normality divided by valency factor. Valency factor is 2 and molarity of HNO3, that is equal to 3 divided by 1, which is 3. So we got the molarity of HCl, molarity of H2SO4 and molarity of HNO3. And what is the volume of HCl also we got that, which is equal to 10 ml. Here volume of HCl is H2SO4 volume is 20 ml and here volume of HNO3 is 30 ml. So if we multiply these two, so I will get the number of moles here. So number of moles of HCl will be equal to 10 and here number of moles of H2SO4 will be equal to 1 into 20, which is 20 millimoles. Here it is 10 millimoles. And here number of moles of HNO3 will be equal to 3 into 30. 3 into 30, which is 90 millimoles. Correct. Now, what about the number of moles of H plus ions? H plus ions and HCl will be same, which is 10. Here, number of H plus ions will be equal to 20 into 2. Why? Because every H2SO4 will give you 2 H plus ions. So, therefore, number of H plus ions will be 20 into 2. Here, number of H plus ions this can generate is 90 into 1. So, therefore, total number of H plus ions will be equal to 10 plus 40 plus 90. So how much we have? 140. Clear? I'm hoping that all of you got this. If this is the total number of moles of H plus, and what is the total volume? Total volume is 10 plus 20 plus 30, which is 60 ml. This is millimoles, 140 millimoles. So therefore, concentration of H plus ion will be equal to total H plus ions divided by total volume, which is 140 divided by 60. 140 divided by 60. So how much we are getting? So that is 2.33 molar. So that is the final concentration. Okay. Or If you want to calculate the pH, that will be equal to minus log of H plus ion, which is 14 by 6. 14 by 6 is minus log of 7 by 3. So which is equal to log of 3 minus log of 7. Alright. Log of 3 value 0.78 minus log of 7 value is 0.85. So 0.85 minus 0.48. So which is minus 0.37. So that is the pH value. Please note it, everybody. Anyone has any problem with solving, please let me know. Right. Shall we go ahead? Now, see the next one, which is about mixture of weak acid and strong acid combined together. Have you noticed the above one is all three strong acid, strong acid, strong acid, and strong acid. Instead, what I'm doing, now I'm adding one strong acid and one weak acid. Then what will be the situation? How do we calculate the H plus ion concentration? Okay. So let's see this. Suppose if you have a weak acid HA and a strong acid something like HCl, the weak acid initial concentration is C naught. It possesses an ionic ionization constant as Ka. And let us say HCl was added to it. HCl was added to it. And the amount of HCl that you are added is Y molar concentration. Of course, HCl does not remain as HCl anymore. It will instantly ionize. All the Y will be lost into the formation of H plus ions and Cl minus ions. So now we will have sufficient H plus concentration and Cl minus concentration already. Got it? Now check this out, everybody. For a weak acid, generally what do we write? We write this as C naught concentration initially, correct? And then we say that H minus and H plus and A minus is not there, correct? But when the HCl is added to it, clear? Then what would happen? I can say this time I will read it like this: C naught. This will be Y and this is not there. That is when HCl is added. HCl is added to HA. Then we cannot ignore that already there is an H plus ion present in the solution. Is this point clear, everybody? Okay. And now what I can say, when the equilibrium is achieved, this will become C naught minus C naught alpha, or let me write down in terms of X and Y first. So some X moles are lost here, or X concentration is lost. So this will become Y plus X and X. Okay, Y plus X and X. If you write in terms of alpha, I can write this as C naught minus C naught alpha, clear? And this will be Y plus C naught alpha, and this will be C naught alpha. This is what you will get. And now, what will be the K value? K value will be equal to H plus ion concentration into A minus ion concentration divided by HA, which is equal to Y plus C naught alpha y plus C naught alpha concentration multiplied by C naught alpha concentration divided by C naught minus C naught alpha concentration. Okay. You know for the fact that alpha value will be very, very, very weaker this time. I mean, very less value this time. Why is that? See, just go back to the Lee-Shatner's principle in chemical equilibrium when we studied. In an equilibrium, in an equilibrium mixture, if a product concentration is more, the reaction will be driving more on the backward direction. And you know that H plus concentration is already more because of the addition of HCl. Okay, when you added HCl. So because H plus is already present in a sufficient quantity, there is mostly the equilibrium lies on the left hand side, which means there is hardly much dissociation observed. Therefore, it implies that the alpha value is extremely low. Okay, clear. And since alpha is very, very small, I can say that C naught alpha value will also be much smaller than Y in most cases. In most cases, I can say that the C naught alpha value will also be much smaller than Y. In most of the cases means examples where you will be given, you will always try to see that the C naught alpha concentration is much smaller than Y. Okay. So if that is the case, you know that alpha is very, very small. C naught alpha value is C naught alpha value will also be way, way smaller than C naught value. So where and what can be ignored? Check out. First, this can be ignored. Sorry. First, this can be ignored in front of C naught, and this can be ignored in front of Y. Therefore, we can write Ka is equal to Y multiplied by C naught alpha divided by C naught. So you can see C naught will get cancelled. It will be simply Y into alpha. So alpha is equal to Ka by Y. Okay. So very important, in most of the cases, you will always notice alpha can be calculated simply as Ka by Y. Okay. And how much will be the H plus concentration? See, H plus concentration here will be equal to Y plus C naught alpha. But we already learned that the C naught alpha can be ignored. So hence, whatever be the HCl concentration that you have added, it will be the same as the pH of the solution. Okay. See, unless the H plus HCl addition is extremely, extremely poor concentration, then we cannot ignore these two terms. But otherwise, like I said, in most cases, you can always ignore C naught alpha and accordingly you can calculate what is H plus concentration. Okay. So I have written that here. You can see due to common ion effect of H plus, dissociation of Wa decreases. Hence, alpha value is very, very small and less amount of ions are formed. Okay. So everybody make a quick note of it. Everyone check. Can I go ahead? Right. Let's see this question. 20 ml of 0.1 molar HCN is mixed with 50 ml of 0.01 HCl. If Ka value is given, find the H plus ion concentration. Find the H plus ion concentration. Instead of directly giving the concentration term, here I have given in terms of volume and concentration, which means while writing the equilibrium, you have to be slightly careful. See, HCN aqueous, it is in equilibrium with H plus and Cn minus. Now write everything in terms of initial number of moles, which is 20 into 0.1 millimoles. And how about H plus? See, HCl will be completely ionized into H plus and Cl minus, which means if you have 5 into 0.01, this entire thing will be ionized into 5 into 0.01 and 5 into 0.01. So which is 0.05 millimoles. So let me write down that. That is initially we already have 0.05 millimoles. Okay. So this is the value initially what we have. So which is 2 millimoles. This is 2 millimoles. And here we have 0.05 millimoles to start with. Clear? If we divide everything by V, total volume, we will get the concentrations, correct? So first let me write down 2 minus, let's say some X moles have been lost from here. So that will become 0.05 plus X and X moles here, correct? And how do we write in terms of concentration now? Now let me write down in terms of concentration. So concentration will be equal to 2 minus X divided by total volume. And how much is the total volume here? 20 plus 5, so 25. Here also 0.05 plus X divided by 25. And here also X by 25. Correct. Now, before writing any further, there are two important things you can see. Ka as it is very, very small value. First of all, Ka is a very, very small value. That is the first thing you need to understand. Second, K value is small. And then if you notice the H plus ion concentration, that means you can uh, uh, remove out this X here. Okay. So X has been released out. So how much will be the leftover now? So therefore, you will have this as Ka value. I mean, this X can be ignored here. So X is way far smaller than 0.05. Thus, therefore, the pH value, sorry, the H plus ion concentration totally will be simply 0.05 divided by 25. So that's it. So 5 by 25 into 1 by 100, correct? So that is equal to 1 by 500. So this is the value of H plus ion concentration. So what will be the pH value here now? Minus log of 500, which is equal to minus log of 500 means sorry, plus log of 500. So which is equal to 2 plus log 5. So that is equal to 2 plus 0.7 or 2.7. So the pH of this solution will be 2.7, and that is mainly contributing because of HCl. HCl's contribution is ignorant. Clear?
Sir, why plus log 500?
It is minus log of 1 by 500. 1 by 500 means it will become plus log of 500. Done? Everybody clear? Now, let's understand the next concept, which is about mixing of two weak acids. So far, we learned how to calculate the pH of strong acid, mixtures of strong acids, mixture of strong acid and weak acid. Now we are trying to find out mixture of weak acid and weak acid. Okay. So if you have both weak acids or if you have both weak bases, then how do we calculate the pH? Check this out. Assume that we got two acids here. One acid is HX1 and HX2. These are the two acids. Both of them are weak. Both have initial concentration C1 and ionization constant as K1. Concentration C2, ionization constant as K2. And these concentrations are after the mixing. It is not before mixing. Okay. After the mixing, their new concentrations are C1 and C2. Okay. Keep writing along with me, everybody. So check. Initially, at time t equal to 0 and time t equal to 0. So I can say that initially this was C1 concentration. This was C2 concentration. At equilibrium, now this will become C1 minus some X amount. This will be releasing some X amount and X amount. At equilibrium, here this will become C2 minus some Y amount lost. This should become Y amount. But you notice that in the solution already there is some X amount. And here also I should be able to view that as Y amount present. So this is important, that H plus ion concentration will be sum of the sum of the contributions from HX2 and HX1. Clear, everyone? Now notice K1 this time will be equal to X plus Y, which is product concentration, into X divided by C1 minus X. Similarly, K2 will be equal to X plus Y into Y divided by C2 minus Y. This will be the concentration. And you know that X value will be far lesser than C1. Y value will be far lesser than C2. Why is this happening? Because H plus is coming as a common ion for both of them. And you know that if the product concentration increases, reaction will go in the backward direction. So that's why in both the cases, you will notice that the reaction is going in the backward direction. Okay. Hence, I can say K1 value now will be equal to X plus Y multiplied by X divided by C1. And K2 value will be equal to X plus Y multiplied by Y divided by C2. So from here, can you notice something? We are getting it as K1 C1 is equal to X plus Y into X, and K2 C2 is equal to X plus Y into Y. Thus, you can notice that K1 C1 plus K2 C2, if I add them, I will get this as X plus Y whole square, isn't it? That implies X plus Y concentration, or X plus Y is nothing but H plus ion concentration, is equal to under root of K1 C1 plus K2 C2. This is how you calculate the H plus ion concentration if you have two weak acids. Clear? Right. So once you get this H plus ion concentration, now what will be the value of alpha? So alpha value will be equal to, see, alpha 1. Let me write down alpha 1. That is ionization constant of this acid. Alpha by definition is amount lost divided by initial amount. Correct? So that is x by C1. This is alpha. And alpha 2 will be equal to y by C2. Correct? X by C1 and y by C2. Clear? And have you noticed something? From here, can I calculate x? And how do I calculate x? Check it out. X is equal to K1 C1 by x plus y. And here y is equal to K1 C1, sorry, K2 C2, K2 C2 by x plus y. Therefore, alpha 1 will be equal to K1 C1 by, clear, uh, K1 C1 by C1 into x plus y, and alpha 2 will be equal to K2 C2 by C2 into x plus y. And you know that you can clearly notice that here we can calculate, cancel C1 C1, and here we can cancel C2 and C2. So therefore alpha 1 is equal to K1 by x plus y, and x plus y we have already calculated. So K1 by under root of K1 C1 plus K2 C2, and alpha 2 will be equal to K2 by under root of K1 C1 plus K2 C2. That's how we can get alpha 1 and alpha 2. Everyone, please check how to calculate H plus ion concentration. So I'll just mark the important points in here. So how to figure out H plus ion concentration for mixture of two weak acids. Next, how to find out their degree of dissociations. One is alpha 1, the other one is alpha 2. Will we go ahead? Everyone, please check. If there is any doubt, you can ask me. Otherwise, we can go ahead. Right. Now, see this case, everybody. Do you remember something? I told you that if the H plus, this is what I told you, right? H plus ion concentration is less than or equal to 10 raised to power of minus 6. Sorry, earlier I wrote it as 10 raised to power of minus 5. Just correct that. It should have been 10 raised to power of minus 6 here. Minus 6. In fact, 10 raised to power of minus 5 is not a problem. It will be much more precise value. But for our NCRT questions and what is being asked in JEE mains, most of the questions they fall under this category of 10 raised to power of minus 6 and above or below. Okay. Let's come to this point. See, as long as H plus ion concentration is less than or equal to 10 raised to power of minus 6, do not ignore contribution from water. That is the first point. If it is greater than 10 raised to power of minus 6, ignore the contribution coming from uh, H plus coming from water. Okay, clear? This is what we need to do. This we have already done. The first two cases, sorry, the first case we have already done. Okay, I by ignoring the water here. Clear? Let us do the second case and third case now. Everybody clear? So, as the H plus ion concentration coming from HCl keeps decreasing. Now notice what is the pH value here. First, let me write the pH of this particular case, which we have already done. We got this as 2 minus 0.6, which is 1.4. This is what we got earlier. Next, check out here. First, 10 raised to power of minus 4 molar. Now, which means the H plus ion concentration of the HCl is 10 raised to power of minus 4, while H plus ion concentration from water is 10 raised to, that will be 10 raised to power of minus 7. But have you noticed this? This value is greater than, 10 raised to power of minus 6. So, in such cases, what did we learn? We can ignore the contribution from water. Thus, what is the H plus ion concentration now? The H plus ion concentration of the solution will be same as HCl, which is 10 raised to power of minus 4. Hence, we can take pH is equal to 4 as the answer. Okay, pH is equal to 4 as the answer. Second, if you have 10 raised to power of minus 8 molar of HCl, then what do? Check out the H plus ion concentration coming from HCl is 10 raised to power of minus 8. Correct. And that is less than 10 raised to power of minus 6 molar. And H plus ion coming from water will be somewhere close to 10 raised to power of minus 7. Correct. Now, do we have to simply add this? Well, don't add that directly because water is in equilibrium. Correct. And equilibrium is subject to change whenever there is a concentration of, H plus concentration added. So now let's see how do we solve it. Okay. So we are solving it for the third part. Everybody look into that area. So for third part here, check. You know that H2O liquid, it is in equilibrium with H plus ion concentration and OH minus ion concentration. Correct? Initially, forget about what is water, but initially, you know that 10 raised to power of minus 7 and 10 raised to power of minus 7 concentration it has in this water. But then what happened, after some time t, that means you added, HCl. On adding HCl, you have actually added plus 10 raised to power of minus 8 molar here. You have added 10 raised to power of minus 8 molar here. Correct? Now, when you added this 10 raised to power of minus 8 molar, correct? See what will happen in that case. On adding, I'll do one thing, just put the continuation here only. Okay. Now the total amount what we have is 10 raised to power of minus 7 plus 10 raised to power of minus 8 and here 10 raised to power of minus 7. This is the total amount of concentration of H plus and OH minus. But notice that if the H plus ion concentration increases, what should happen? The equilibrium will shift onto the backward direction, Le Chatelier's principle. Right, everybody? So let me write down that. As H plus ion concentration increases, reaction, the equilibrium equilibrium will shift in the backward direction. So imagine if it moves in the backward direction, what would happen? That means out of this, some X amount will be lost. Some X amount will be lost from here. Correct? Out of this, some X amount will be lost and X amount will be lost from. So what is the concentration of H plus ion concentration at equilibrium now? At equilibrium, now you will get 10 raised to power of minus 7. Let me write down this way. 10 raised to power of minus 8 plus 10 raised to power of minus 7 minus X. And what will be the OH minus concentration at equilibrium? It will be 10 raised to power of minus 7 minus X. Have you noticed this 10 raised to power of minus 7 minus X and 10 raised to power of minus 7 minus X is common term in both of them? Let me use that value as 10 raised to power of minus 8 plus some Y. So here also 10 raised to power of minus 7, and this will be Y, correct? So what do we know for sure? We know for sure that the Kw value will always remain constant, which is H plus ion into OH minus ion concentration. So that is equal to 10 raised to power of minus 8 plus Y into Y. That should be equal to 10 raised to power of minus 14. Make it into a quadratic equation now. So what do I get? I'll get this as Y square plus 10 raised to power of minus 8Y minus 10 raised to power of minus 14 equal to 0. So what will be the value of y? So y will be equal to minus 10 raised to power of minus 8 plus or minus under root of b square, which is 10 raised to power of minus 8 whole square minus or 4ac. So 10 raised to power of minus 14. That divided by 2a. Okay, so 2. So from here I can get y is equal to minus 10 raised to power of minus 8 plus under root of, if you notice, this is coming as 10 raised to power of minus 16 and this is minus 14. So I can write this as 401 into 10 raised to power of minus 16 divided by 2. So which is minus 10 raised to power of minus 8 plus, I can assume this as almost 400. So the root of 400 is around 20 into 10 raised to power of minus 8. That divided by 2. So therefore, y value what I'm getting is, you know, 19 by 2 into 10 raised to power of minus 8, which is 9.5 into 10 raised to power of minus 8, or 0.95 into 10 raised to power of minus 7. So this is the value of y, everybody. Okay, this is the value of y. Now check out what is the H plus ion concentration, everybody. So H plus ion concentration will be equal to 10 raised to power of minus 8 plus 9.5 into 10 raised to power of minus 8, which is equal to 10.5 into 10 raised to power of minus 8, or simply 1.05 into 10 raised to power of minus 7. Okay, so how much will be the pH value? pH value will be equal to minus log of 1.05 into 10 raised to power of minus 7. So which is equal to 7 minus log of 1.05. You know that log of 1.05 is very log of 1.05. Okay, so that is very close value. So that is 7 minus 0.02. So that is 6.98 approximately. So what is that to be noted? That it is still less than 7, and that is what we expect, right? An acid always has to have pH value less than 7. So check out how do we need to calculate the pH of very dilute solutions. So for very dilute solutions, everybody, what you will be asked is that, you need to know for sure that the pH value will always remain less than 7 if it is acid. pH value will be always greater than 7 if it is base. Did everybody made a note? Now, just by watching this, you should be able to tell me what will be the pH value. Okay, it will be greater than or less than. What will be that? Okay, so check out for pH 10 raised to power of minus 10, such a low volume. So I can say that pOH value will be very, very close to 6 point something like 995, because it has to be slightly less than 7, which means the pH value, correct? pH value will be very, very close to 7 point something like 001. That is the option. Here you don't need to, you are not expected to solve and find out the values. You will be given the options like that. So you need to choose the correct options, close by options. Okay. So the pH you should search for this kind of cases will be very close to 7 point, 001 or 7.003, whatever the options are given. Similarly, 10 raised to power of minus 10, the same logic, the pH value will be very, very close to 6.995. So this will be very close to 6.995 like this. And the pOH value will be very, very close to 7.001. Okay, 005 or 001, 2, anything. Okay, I'm just taking an appropriate approximate value close to that. Same 10 raised to power of minus 7, if you have, again same logic, pH value, pOH value should be quite less than something like 6.95 like this, and pH value will be 7.05 like this. Okay, this is the value we can have. Same way, if you have 10 raised to power of minus 9, pH value should be something like 6.98, clear? 6.98, and pOH, this is close by 6.98, and pOH will be equal to 7.02 like this. Okay. These are the values. Right, everybody? So for very dilute solutions, if the accurate value is been asked, you have to solve the quadratic equation. If the range is asked in the question, you can simply find out, what is the closest value and attempt that. Right. Now, everyone, look into this case. Suppose if I'm talking about an acid-base reaction, correct? Acid-base reactions will always lead to the formation of salts. For instance, if I take HCl add with NaOH, we expect NaCl and water, salt water. Likewise, if I have a base, weak base like ammonium hydroxide and HCl, here also I'll expect the ammonium chloride salt. Acetic acid and NaOH, weak acid, weak base. I'm expecting sodium acetate salt. Formic acid, ammonium hydroxide. So ammonium formate. This is again a salt. So ammonium hydroxide, H2SO4, that is ammonium sulfate, again a salt. Hydrogen, I mean, this is oxalic acid, NaOH. You'll get sodium oxalate. This is a salt form. So whether it is a strong acid, weak base, weak acid, strong acid, strong base, any combination, what is the learning here? That reaction will definitely happen and it will form salt and water. Okay. So whether it is a strong, weak does not make any difference. The reaction will bound to happen. Correct. Imagine if I take the equal quantities, everybody. Suppose if I take X moles here and X moles here. So nothing will be left here. Everything will become salt. Now you might ask, sir, what if you have weak and weak, X and X? Even if it is weak and weak, both will get completely reacted and you'll get salt. So for neutralization, it does not matter whether you have strong or weak species. Everything based on their proportionate amounts, it will convert into salt and water. Clear, everybody? Now, if that is the case, then we will expect a concept called hydrolysis. Lysis, okay, a Greek word which means breaking, correct? Which means you are trying to break water molecule. Hydro means water molecule, lysis. So henceforth, wherever you see this term hydrolysis in organic reactions or everywhere, it meant that you are trying to break the water molecule. Got it? And I added another word here, salt hydrolysis, which means salt is the reason why there is a breaking of water. That's why it is called salt hydrolysis. Clear? Now notice phenomena of breaking the water molecule is salt hydrolysis. Either the solution will become acidic or basic after the breaking of water molecule. Okay, once the water molecule has been broken, it might become an acidic solution or it might become a basic solution. For example, strong acid and strong base, if you have added, you will get a salt, like in this case, right? When it comes to HCl, and if I take NaOH, after reacting, you will get it as a salt. Now notice, when you have salt added, NaCl added to water, do you notice that either Na plus or Cl minus breaking water molecule? No, you won't see that. Which means Na plus and Cl minus is not able to break or do hydrolysis. Okay. So what is the learning from here? Notice, if any strong acid or a strong base is present in salt as a part of salt, they what do you say? They do not make any hydrolysis. But if the acid or base which is present as the conjugate acid or a conjugate base, that will undergo hydrolysis. Okay. For example, check out here. See, Na plus is anyway spectator, so that is why I'm not writing Na plus on both sides. Hmm. So if at all I have a strong acid like HCl, strong base like OH minus, react both of them, I will get water and Cl minus. And Cl minus is a conjugate weak base, right? Since it is a weak base will not have strength to break water. Understood? Hence, we say that there is no salt hydrolysis observed in the case of strong acid, strong base prepared salt, which is, and salt which has been prepared from strong acid, strong base, it will not influence the water to break. Clear? But if you have weak acid, strong base, now problem what happens is the strong base has converted into a weak acid, which is water. But this weak acid, after the reaction, is converted into strong base. So now this strong base part which you have, CH3CO minus, this will have enough basic strength, that will have enough strength to break the water molecule. Hence we say that sodium acetate salt will give salt hydrolysis. Everybody clear with this fact? Clear? Now let us understand when it is breaking water molecule, what all new equilibriums that are being established. Correct? What are all the new equilibriums that are getting established? Correct? So notice this one. We have a salt concentration here. I mean salt ion, which is CH3CONa, sodium acetate salt. Okay. Imagine it is a white color powdered salt. You have it with you. You added it to water and mixed it. First of all, it is a white color salt. Immediately, as soon as you add to water, it will ionize completely. Which means if its concentration is C naught, that entire C naught will convert into C naught of this and C naught of this. Now we have a strong base concentration in the aqueous solution, which is of C naught concentration for acetate. So check out. Now what will acetate do? CH3CO minus aqueous, which is present in water. will interact with the water molecules, try to break it and attain an equilibrium. And as it breaks, you will get this as CH3COOH, because this minus will try to take H plus from water. And what is left over? The leftover part is OH minus. Hence, the OH minus is being released. And this equilibrium is what we call it as hydrolysis constant. So KH here will be equal to hydrolysis constant. Imagine initially we had C naught concentration before the lysis happening. Now at equilibrium, from C naught some X amount has been lost. So what do we get? Here we will get this as X amount of acid and X amount of OH minus. How, just like degree of dissociation, here we are defining a new term known as degree of hydrolysis. Degree of hydrolysis, which is H. H is equal to amount lost, just like alpha, amount lost divided by amount initial. Amount initial. So that is equal to how much is the lost amount? X divided by C naught. So from here I can write C naught X is equal to C naught H. So therefore this equilibrium can be written as C naught minus C naught H, C naught H and C naught H. And how did we define KH? KH is a hydrolysis constant, which is CH3COOH concentration multiplied by OH minus concentration divided by CH3COO minus concentration. Therefore, it is C naught H whole square divided by C naught minus C naught H. So you can see one C naught will get cancelled. So we'll get this as C naught H square by 1 minus H. Again, for most cases, for most salt hydrolysis, the H value is quite smaller than 1, which implies KH can be written as, simply C naught H square, or H, that is the degree of hydrolysis, can be written as KH by C naught. So I suppose up to this point, everybody is clear there. So we got hydrolysis, degree of hydrolysis as under root of KH by C naught. Now notice this part. Whenever we have an acid forming in the solution, the acid will always have something here. That means it will always try to maintain an equilibrium with its own ions. That is CH3CO minus plus H plus. So that means this equilibrium will always be existing, which will be Ka. Likewise, water will also always maintain its equilibrium. That is H plus ions and OH minus ions equilibrium. And that we define it as Kw. Now, if this is Kh, what will be Ka and Kw? Ka will be equal to CH3 COO minus into H plus ion concentration divided by CH3 COOH. Likewise, Kw will be equal to H plus ion concentration into OH minus concentration. So from here, if you compare KH, right? KH, if you notice that, if you check out KW, you're actually getting this as a multiplication of KH and KA. Notice this carefully. This multiplied by this. If you multiply that, this CH3COH will get cancelled. Then CH3CO minus and CH3CO minus will get cancelled. So this will lead to the formation of H plus ion concentration into OH minus ion concentration. Okay. So that implies KH can always be replaced as KW by KA. Okay. This you have to remember as a part of derivation. Very important. how to represent KH in terms of KW and KA. In most questions, directly KH value is not given, but you know how to relate KH with KA and KW. Okay. Now our objective is to find out what is the value of OH minus concentration or H plus concentration. As per the solution, you can see OH minus concentration is C naught H. So that is OH minus concentration is equal to C naught H. And H we learned it as under root of KH by C naught, which is equal to under root of KH into C naught. And KH we just learned can be written as KW by KA into C naught. Correct? Hence, OH minus concentration can be written in these terms. So, if at all I write this as POH, POH is equal to half of, because that root can be written as half, into minus log of KW minus log of KA and minus log of C naught. That is equal to half into, this is PKW minus PKA minus log C naught. This is what you will have as POH. Now what will be pH? pH will be equal to 14 minus POH. So that is 14 minus POH is half of PKW minus PKA minus log C naught. Can I write 14 as simply PKW? Because 14 is nothing but PKW. So PKW minus of this entire thing minus PKW minus PKA minus log C naught. So this is 14 minus 7. 14 minus 7 is again 7, which is half of PKW. Thus, pH will be equal to half of PKW plus PKA plus log C naught plus log C naught. So this is the, you know, derivation for pH calculations. This is the pH calculation, and you notice this pH value will be always greater than 7. Why? Because now the solution has turned basic. Since it is basic, it has to be always greater than 7. And this is for which derivation? For weak acid and strong base salt. So when the salt is made out of weak acid and strong base, this is how you calculate the pH. Okay. So please check the derivation, everybody. If there is any problem, I can discuss with you. Done? Now, before going into the question, check it out. Which salts which qualify for hydrolysis and that are coming from weak acid and strong base. Weak acid and strong base. Check it out. Suppose if at all I have NaF, that will definitely qualify. BaF2 definitely qualifies because barium hydroxide is a strong base. HF is a weak acid. Got it? So if you notice these cases, definitely they will qualify. KCN definitely qualifies because it is coming from KOH, which is a strong base, and HCN, which is a weak acid. Correct? Everybody, like this. any weak acid you take and you just join that with its conjugate basis. For example, if you have other acids like NaNO2, HNO2 is a very weak acid. NaNO2 will make it the salt that is important for it. Clear? Like this, I have NaOCl. HOCl is a weak acid. Okay. Now all organic acids like HCOOK, potassium formate. So it is coming from a weak acid and a strong base. Clear? So any RCOO minus combined with a potassium or sodium, that means they are always going to be weak acid and strong base combinations. Clear, everyone? Right. Similarly, if you have KClO3, HClO3 is a weak acid, so that makes it as definitely qualifies for this hydrolysis. Okay. So if at all you see these type of combinations, everybody, so you should know that these are all going to give us salt hydrolysis. Okay. Now, come to that particular type of question now. Check it out. Find the pH of 0.05 molar salt, sodium formate salt, if the pK value of acid is given as 3.8. Okay. So first you need to check whether the salt will qualify that or not. So it is definitely qualifying because it is coming from NaOH and HCOOH. So formic acid is weak, NaOH is strong. So using that concept, now I can say that pH here, so I can write that pH here will be, we can use the formula pH is equal to half of pKw plus pKa plus log C naught. So that is equal to half of pKw is 14 plus pKa is 3.8 plus log of 0.05. That is equal to half of 17.8 and that will be log of 0.05 will be equal to 2 minus point 2 minus 0.7, which is 1.3. So that makes it 16.5 divided by 2, so which is 8.25. So you can notice that it is greater than 7 and it has to be greater than 7, correct? So that the solution now has turned out to be basic, correct? So that will be the value of pH. Everybody clear how to use it directly as a formula? Everyone, please try to address this part more carefully. What is this C naught here? C naught is not actually the salt concentration, it is the salt ion concentration, like this. For example, if you have HCOO minus Na plus, that is completely ionizing into HCOO minus plus Na plus. So because this is 0.05, we are expecting this to convert into 0.05. So actually this is C naught value, okay? And because the C naught value is matching with the salt concentration, we simply say it as a salt concentration. But to be precise, it is not salt concentration, it is a salt ion concentration. Why that is important? See the next question here. The pH value of this particular salt we need to figure out. So it is coming from a strong base and a weak acid. So how does it split into? So you know that when you have barium acetate, CH3CO twice, barium, as it dissociates in water, 100% it will dissociate into 2 moles of CH3CO minus plus barium 2 plus. Now, if this is 0.1 molar concentration, this will get completely over. But how much you will get? Here you will get 0.2 molar. And this is your C naught value. So, clear? So that is where you need to be little cautious. So C naught value is not directly salt concentration. It is the salt ion concentration which is undergoing salt hydrolysis. And now you can calculate pH easily. pH is equal to half of pKw, which is 14, plus pKa, which is 4.8, plus log of C naught value, which is 0.2. So half of 18.8 plus minus 0.7. So which is 18 point 18.1 divided by 2, so which is 9.05. So that is the pH of the solution. Of course, it is greater than 7. That is what we expect. So everybody, you need to recognize what is the salt that is being used, and you need to figure out how to calculate the pH of that salt. Then see the next case here. Check. 200 ml of this acid is titrated with this much amount of NaOH. Find the final pH of the solution. Okay. Now, how do we solve this kind of question? First, write the reaction, everyone. Write the chemical reaction. See, it is like this: CH3 COOH plus NaOH. It is making a titration to form a salt, which is CH3 CO minus Na plus H2O. Okay. So what are the number of moles do we have? We have 200 multiplied by 0.2, and we have 200 multiplied by 0.2, which means it is completely neutralized. So there is no more salt, sorry, no more acid, no more base left. Everything is converting into salt. So that is 200 into 0.2 millimoles of acetate ions. Okay. So now what do we have in the solution? Only salt and water we have. And what is the salt ion concentration? That is CH3CO minus is the salt ion concentration, which is 40 millimoles divided by total volume. What is the total volume we have? So we can say it is 200 plus 200, total 400. So 400 ml. So which makes it 1 by 10 molar. So which is 0.01 molar. Sorry, 0.1 molar. So this is the C naught value, everybody. So we got the C naught value. Now listen up, salt hydrolysis is a formula that you will apply only when salt is present. There should not be any acid or any base left in the solution. Correct? Only we should have salt and water. And this is a typical case where there is only salt and water, because after titration, neither acid nor base is left. Okay. Hence, how do we calculate pH now? So pH is equal to half of pKw plus pKa plus log C naught. So half of pKw, pKw is 14 plus pK value is 5 given, and log of 0.1. So that is equal to 19 minus 1, 18. 18 by 2 is 9. Hence, pH of this solution is 9, which is definitely greater than 7, and that's what we expect. Everybody clear? Any doubt from this part? Anna, Ayushi, Pratisha, any problem at all?
No, sir, no problem.
No,
No,
sir.
sir.
Very good. Right, everyone. So we'll stop the session here now.